Hi, this is Professor Fernandez. We are going to work on class notes E in lesson 14. This class notes picks up where the previous one left off. You can see that V originally in this example is the set of solutions to this CC sold. And rather than walk through how to write that in vectorial form, I've just given that information to you here. And actually what I'm asking you to do is much more sophisticated. So I want to find a basis of vector valued functions for this set. All right. So that's, first of all, pretty neat because basis, that's a linear algebra concept. And this set is a set of vector valued functions that satisfy a system of differential equations. So this is kind of the first time that we're really marrying these two concepts, linear algebra and differential equations. From our linear algebra lessons, we know that to find a basis, we have to show that it's linearly independent and that it spans. Okay. So from our linear algebra knowledge, we are going to figure out, how to do one of these two, and it's not clear where to start. So I'm going to start in the way that we do know how to start, which is we have a second order ODE, and we can solve that. Okay, and then I'm going to write down the connection that we've been using between the ODE and the system, right? We know that x1 is y and x2 is y prime, and that the vector valued function x is x1, x2, which in this case is y, y prime. Okay, so first of all, let's talk about y double prime plus 4y equals 0. So this is a CC solved, which we learned how to solve, I believe, in lesson 5. And in lesson 4, we learned how to solve the general CC solved, but this is going to end up having complex roots. So anyway, the characteristic equation here is r squared plus 4 equals 0. If we try to solve here for r, we are going to end up taking the square root of a negative number, which is okay in this class, right? Because that gives us complex numbers. So plus and minus 2i. Remember that the solutions we get from here, we only take the number with the positive imaginary roots, and then we write it in the form alpha plus beta I. We look at its real part, we look at its imaginary part, and we get two solutions. We get y1 of t equals e to the alpha t, but in this case, the real part here is 0, so e to the 0t. Cosine of the imaginary part, which is 2, cosine 2t. And then y2 ends up being e to the alpha t again, times sine of beta t. All right, so if I simplify what's happening here, then y1 of t is cosine of 2t. y2 of t is sine of 2t. Right? And then based off of all the work we did in the second unit in the course, right? All the theory we built up for second order ODEs. The general solution to y double prime plus 4y equals 0, we know is y of t equals linear combination of these two fundamental solutions. Right? So we know that from the second part of the course. Okay, so at this point, it seems like I've just disregarded what lesson we're in. We're in lesson 14. There's a vector valued function that we're supposed to be talking about up here. So now let's get back to that, right? Remember, the y that we have found is, the same y here. That's x1. So what I have just been able to find, to show, is that x1 of t, which equals y of t, equals c1 cosine of 2t plus c2 sine of 2t. Okay, and I'm going to sort of, emphasize this because it's very easy to not realize how important this is. X1 equals y is how we convert, again, between the original ODE, here it is right here, the original ODE, and this system form. When we do that conversion, we don't know what x1 is because we don't know what y is. But now that we have solved the ODE and gotten the general solution, which means that every y is a linear combination of these two, we know what x1 is, right? x1 is literally that linear combination. Okay, so now x2 we also have information about. Our substitution tells us that x2 of t is y prime of t. I'm going to scroll up here, right? That's exactly how we got this system. There it is, x2 is y prime. So what am I going to do? So I'm going to take this c1 cosine plus c2 sine and just differentiate it. So a little chain rule there gets me sine of 2t, and then another chain rule here gets me cosine of 2t. Okay. So therefore, the vector valued functions that are in this set V, right? They have this particular form. Remember, they had the form y of t, y prime of t. That came up from here. And I now know what y and y prime are. c1 cosine of 2t plus c2 sine of 2t. And then this one is minus 2c1 sine 2t plus 2c2 cosine 2t. Oops. Okay, so I'm going to remove some clutter while I tell you what we are going to do next. So we have just shown that the vector valued functions that are in this set V that solve the vectorial form of y double prime minus 4 plus 4y equals 0 have the form that we just wrote down here. Great. So now to get back to what we were asked to show in the problem, right? We've been making progress on that. This exercise asked us to find a basis for the set V. Okay, so what we have just found is going to help us do that because we now we can rewrite the set V, right, as the set of vector valued functions that look like this. Great. So I'm going to take this representation of V over here, and then I'm going to say, oh, x of t is, I'm going to decompose it. So I'm going to try to break up this one vector into just this vector plus that vector. And I can certainly do that. So I'm going to write c1 cosine of 2t, and then minus 2c1 sine of 2t. Great. Plus this other vector, c2 sine 2t, and then 2c2 cosine 2t. And then notice that this first vector, both components have a c1, so I'm going to factor that out. And I'm going to get cosine of 2t, and then minus 2 sine of 2t. And then this second vector, both of these components have a c2. I will factor that out, be left with this. Okay, and then I'm going to introduce some new vectors here, right? So all of this work has shown us that the x of t vector valued solutions all have the form c1 x1 of t plus c2 x2 of t, where this is x1 and this is x2. All right. So if we kind of stop thinking in terms of differential equations and we put on our linear algebra hats, what we have just shown is that if x of t is a vector valued solution to the system of, in this example, this one, right, then it can be written as a linear combination of x1 of t, x2 of t, right, that one and that one. So with your linear algebra hat on, that tells us that x1 of t and x2 of t span V. So I'll write that here. This shows that x1 of t and x2 of t span V. Okay, so that's nice. So we are halfway done to proving that they are a basis. So what's the next thing I have to do? Well, up here, we did the span, check. We have to do linear independence. So to do linear independence, I'm going to set up the linear independence condition. I'm going to set it equal to the 0 element in this space, which is the 0 vector. and then I want to know whether that implies that all the c's are 0. Okay, so I'm just going to write out what this system looks like. And notice that it's kind of like going backwards, right? The first thing I would write is this. Oops. First thing I would write is this. And then I would combine those two into this. And then I would keep going from there, from where that came from earlier in the notes that I erased. So I would get this vector, c1 cosine 2t plus c2 sine 2t. And then down here, minus 2c1 sine 2t plus 2c2 cosine 2t. And I'm setting this equal to the 0 vector, equals 0, 0. So if I look at each row independently, that's basically like removing the vectors from here and then generating these two equations. So now the next step that I want to do is I want to solve for C1 and C2. So this is a system of linear equations, but it's kind of special because all the linear equations we've been solving in this course up to now, the coefficients have been numbers, but the coefficients here are functions. So how do we do that? Well, we kind of apply the same ideas as before. We could throw this into an augmented matrix. That might be scary, so we won't do that. But we're going to follow the same idea as before, meaning we're going to try to eliminate one of the variables. So the first thing I'm going to note is that there's a 2 here and there's a 2 there. So I'm going to divide by that 2, and that will get rid of the 2. So there we go, the 2 is gone. Okay, and then a second thing I want to notice is that there's a c1 here, there's a minus c1 here. But this is cosine, this is sine. So I can't just add the equations and get rid of the c1 term. However, what if I multiply this equation by sine of 2t? And what if I multiply this equation by cosine of 2t? All right. So this is effectively like doing a row operation. Okay, then so what's going to happen? I'm going to get, on the left-hand side, I'm going to get c1 cosine 2t sine of 2t. And then this sine times this sine gives me a sine squared 2t. Right-hand side stays 0. Second row, I get here minus c1 cosine of 2t times sine of 2t. And then this cosine times that cosine gives me a cosine squared 2t equals 0. And now when I add them, add these two equations, this term goes away, right? C1 minus C1, and now they have the same coefficient, if you will. And when I add these two things on the right-hand side, I can factor out C2, and I get sine squared 2t plus cosine squared 2t. That's 1. So when I add these equations, I get C2 equals 0 plus 0, 0. So that's great. So I get that C2 is 0. And then, of course, taking that C2 and substituting it into any one of these equations gives me C1 equals 0. All right, and that's exactly what we wanted to show for linear independence. So we did Li up here as well. We did Li, we did span. So we have found the basis. And what is the basis for this space of solutions? It's exactly these two vectors here. These two vector valued functions here. Okay, so we're done with the example. I do want to mention one quick thing, just so that things connect a little better for you. Remember, I erased it, but I'll remind you that y double prime plus 4y equals 0 has two fundamental solutions: cosine of 2t and sine of 2t. Right? If we rewind this video a little bit, you'll see where I got those from. Look at the vector valued functions that we found that form the basis for the vectorial representation of this CC solves. Remember, because all the vectorial representations have the form y and y prime, then what can we say? We can say that x1 is like the vector version of y1. Right? Here is literally y1, and then this is y1 prime. Why is it y1 prime? Because all vector valued functions in this procedure have their components y and y prime. Okay, and then here is the second basis element. And what does it look like? It looks like y2, the second fundamental solution, and then its derivative. Again, because that's the structure that all of these vectors have. So in other words, there's a really nice correspondence. This is what the situation looks like at the differential equations level. These are the fundamental solutions, right? And then the general solution is a linear combination of these two fundamental solutions. And then at the vectorial level, at the system of n differential equations level, this is what the general solution looks like. And it happens to be a linear combination of the vector analog of the first fundamental solution and the vector analog of the second fundamental solution. So I just wanted to make that connection for you that, there is this deep translation of fundamental solutions into basis elements. So every time we were using the word fundamental solutions in linear algebra, we were certainly foreshadowing this result, but we can again think of fundamental solutions as basis elements for constant coefficient sols, and their vectorial representations as basis elements for the vector valued versions of those CC sols.